So what is the aldol condensation of this reaction? So let's go ahead and look. I'm going to take this, I'm going to chop it off and stick it on this. So I'm going to end up with this compound with a double bond down here, and then attached to the other end of the alkene will be two propyl groups. Where do I see that? Not enough carbons. Well, I have the right idea here of an ene there, but I only have methyl groups here. There's no ene here, and here you have this carbonyl up there, but you have the double bond in the wrong place. It would be right there. If I look over here, I can see there is my ketone, there's the double bond, and there are the two propyl groups. So that is the correct product. What combination of reagents give this aldol condensation product? Remember to back this up. What we have to do is chop this in half here. So I'm going to look for this ketone, which is going to be 3-pentanone, and I'm going to look for this carbonyl, which would be benzaldehyde. Now, where do I see this? Here I see 3-pentanone, and here I see benzaldehyde. So this is the product I'm looking, the reagents I'm looking for. Which one of the following reactions give this product? I don't even have to look at suggestions. I can just back this up. Cut this here and put a carbonyl there. That's going to give me 1, 2, 3, 4, 5, 6, 7. So it'll be 3, 7 nonadione. So look around for a dione. There's only 3 that are diones. If I look for this, another way I can recognize it is look for the carbons between them. These are all diones, but what about how far apart the ones are? Notice there's 1, 2, 3 methylene groups between them. There are 1, 2, 3, 4, 5. They're 1,5 diones. These are 1,4 diones. These are 1,6 diones. This one's a 1, 2, 3, 4, 5 dione, and this is the 3, 7, I think it was, dione that I had said that by cutting and trying to figure out you would have to have. So this is the correct product, reagent that you need to get that product. You have 4 products made from this mixed aldol condensation. Which one would not be formed? Well, let's go ahead and look at the products and see if we can back them out and see which one. If I cut this, that would give this and this as my 2 ones, so that's one of them. If I cut that, that gives me this ketone and this ketone, so yep. Cut this one, yeah, I get those 2 back. If I cut this one, I get those 2 back. If I cut this, though, what do I get? I get the 2 things, but this can't form because, look, it has to be on the alpha carbon. This is on the beta carbon. That can't form. So that is the correct one. That does not give, is not produced by this mixed aldol. So what are the aldol condensation products that we would get from this dione? Well, I have 1, 2, 3, 4 different alpha carbons. But if I try to form a ring with this, 1, 2, 3, 4, I would make a 4-membered ring. With this, 1, 2, 3, 4, a 4-membered ring. So that's not going to happen. The only 2 that can cause an aldol condensation would be this being the nucleophile with that carbonyl, or this being the nucleophile with that carbonyl. If I go and do a nucleophilic attack here, I would end up getting an ene with a methyl on either, a methyl here and a methyl here on either side of the double bond. That's this one. And if I have this one doing a nucleophilic attack here, I'm going to get an ethyl. Where is that ethyl going to be? It's going to be on the far end of that double bond. So it's not going to be this one, it's going to be this one. So these are the two aldol condensation products that form. So which of the following is the best candidate for a cross-Claisen reaction with ethyl acetate? Well, ethyl acetate has an alpha proton that can be the nucleophile. So to have a cross-Claisen, you're going to have something that has no alpha proton. If I go ahead and look at these, I can see there's an alpha proton here. There's an alpha proton here. There's an alpha proton here. And there's an alpha proton here. And this is really messed up because we've got a methoxy group there. That's going to stabilize a negative charge here. It's going to be a really great nucleophile. But if I look at this one, I can see there's 3 methyls there. That is not going to allow any deprotonation, and so only one Claisen reaction can occur, where with the ethyl acetate being the nucleophile. So this is the best candidate. All the rest have alpha hydrogens. A Claisen condensation is which type of reaction? Well, let's look through. It's not an electrophilic aromatic substitution. In fact, you don't have to have an aromatic ring in there. We see all sorts of Claisen condensations, like ethyl acetate with ethyl acetate. It's not hydrolysis or decarboxylation because we see hydrolysis and decarboxylation after a Claisen condensation, but that's not a Claisen condensation. What is it? It's nucleophilic acyl substitution. What is the product of this Claisen condensation? Well, let's use our trick. Cut this off and tack it onto another one of them right here. So where do we see that? Look for this cut off tacked onto the alpha carbon of another one like this. Okay. There's nothing tacked onto the alpha carbon here. There is something tacked onto the alpha carbon here. Let's look and see if it's the right compound. Well, look, there's a carbonyl, and then 1, 2, and then the phenyl group. This looks like a likely product. Let's check the others. Here is something tacked onto the alpha carbonyl, but we don't have the rest of this there. We need that. Here we have our ester, but this is in the wrong place, and it's just all messed up anyhow. Here, can we have this? Well, we don't have. Where would we get this? I don't know how anyone would think that up. So no, it's not that. What is the correct product here? It's this one. What is the Claisen product here? Okay, well, essentially, this is going to be the nucleophilic. It's set up so easily for you to see it this way. This is going to be the nucleophilic carbon attacking here, and we're going to lose a methoxyl group here. So, boop, that's going to go in there. So we're going to look for a 5-membered cyclopentanone with a cyclohexane ring on the other side of it. Where do I see that? Here is a cyclopentanone ring, and here's a cyclopentanone ring, but it's in the wrong, it's a dione and it's in the wrong place. That's all messed up. That's all messed up. That's all messed up. This is the only one that looks right. So let's go ahead and see if it possibly can be. If this does nucleophilic attack there to form the cyclopentanone, on the alpha carbon to that cyclopentanone, you're going to have this group. Do we have it there? Yes, we do on the alpha carbon. So this is the correct one. Okay, what's the product of this Michael addition? Well, we're going to have sodium ethoxide forming an enolate on this. Where is the enolate going to form? On this carbon, because it's going to be stabilized by this benzene ring. That's going to end up doing 1,4 attack on this conjugated carbonyl. So that comes in here and does 1,4 attack. But that what forms is going to be, you're going to have basically on here, you're going to have 1, 2, 3, 4 carbons, and there's going to be a carbonyl there with a methyl group stuck out real close to this carbonyl that can then do an aldol condensation. This is what we call the Robinson annulation. So where are we going to see that? Right here. You see, this used to be the carbonyl right there. These are those 3 carbons. 1, 2, 3. This carbon right here is this. This is the correct product. So what is the product of this reaction? Notice this is an enamine and a conjugated carbonyl. This is what's called the Stork reaction. What are we going to have? Nucleophilic attack from this carbon right here, because the non-bonding pairs jump in there. These electrons jump there. This does that, and that does that. And then once you have protonation, you're going to have protonation here, and then this is going to be lost, and it's going to return to a carbonyl. So what am I going to look for? I'm going to look for these carbons being attached here and a carbonyl there. So 1, 2, 3, 4, 5. Let's look for it. 1, 2, 3, 4, 5. That's correct, except for we end up getting an imine here, not an amine. And so the arrangement of atoms is correct, except this would be an ene here, and then the water with acid would have cleaved it to the ketone. Let's look over here. Well, this is not going to happen. We're not going to have 1,2 addition here. That's too soft a nucleophile. This is all wrong. This is correct, except 1, 2, 3, 4, 5. This is correct, except for right here we have an ene. That ene is gone because you've had things add across the double bond. So the correct product is this one right here. Go ahead and try to determine what's the outcome of this reaction. Well, this is going to be a mixed Claisen. This can form an enolate, this cannot. So this is going to form an enolate here and do nucleophilic attack here and with loss of ethoxide. So the product that we get is this added to this carbonyl. See how that used to be this over here. This right here, that used to be that. What's the product of this reaction? What's going to happen here is this is going to deprotonate this, make it into a good nucleophile. What do I have over here that can do nucleophilic substitution? Well, that bromine right there, an allyl bromide, that's going to undergo a really fast SN2. So all that's going to happen is we're going to end up getting these 3 carbons added to this carbon here. And this is the product.